am Elisabeta and I will present our work on weakly supervised detection of diffusion-based image manipulations. First, let's have a short test. What do you think of this image? Is it real or fake? If you guessed it was fake, you're right. However, simply labeling it as fake disregards the fact that it is not entirely AI-generated, since only the eyes have been altered, as it can be seen by looking at this mask and the original image. In our work, we tackle the task of deepfake detection, but instead of only deciding whether an image is fake or not, we believe a more informative output would be to pinpoint which part of the image is likely to have been generated. The task of deepfake localization is usually framed as a supervised task in which an image is paired with its manipulated mask. Here, we are interested in a weakly supervised setting in which an image is paired only with a fake or real label. Why weak supervision? First, ground truth masks might not always be available. Second, generative methods are usually first developed in the context of full image synthesis and only then extended to the more specific cases of local editing. Training on fully synthesized images would allow us to be one step ahead of the potentially harmful uses of locally editing an image. Third, weakly supervised localization allows us to quantify the explanation capabilities of binary detection methods. This setup is important since detection models remain the most popular ones. We investigate three categories of architecture suitable for weakly supervised localization. These are all based on the Xception backbone. The first one uses the GradCam explainability method to highlight the most predictive regions for the fake label. The other category is implicitly constructed localization maps. Patch forensics takes the feature activations after a few layers and projects them to a patch level score using one-by-one convolutions. At train time, the loss is computed for each patch, while at test time, it produces a detection score by averaging the per-patch softmark scores. Attention predicts an activation map that is used to modulate the feature maps produced by the network. The network is trained in a multitask setting with a loss on the full image fakeness score and another one on the localization mask, which ensures that the maximum value of the predicted mask agrees with the image level label. We apply these methods on the state-of-the-art generative models represented by diffusion-based techniques and focus our attention on face manipulations since these are the most susceptible to be used for malicious purposes. As real data, we use the two most popular face datasets, celeb-AHQ and FFHQ. As fake data, we consider two types of fake images, fully synthesized and locally manipulated ones. For the fully synthesized data, we use the perception prioritized P2 diffusion method. We can see some examples in the right. For the locally manipulated data, we use the repainting technique. This method works on top of any pre-trained diffusion model. We use P2 and LDM. In order to evaluate localization performance across classes of generators, we also consider data based on autoencoder and GANs, such as Llama and Pluralistic. Some examples are illustrated on the right. Notice that all samples are highly realistic. The impacting regions correspond to various face attributes: skin, hair, eyes, mouth, nose, glasses, and combinations of these. Our experiments evaluate the proposed methods with different levels of supervision, gradually changing the dataset and the generators in order to quantify their importance for localization. We investigate the performance using three main levels of supervision. In scenario A, we use for training fully generated images and a real fake label per image. In scenario B, we use locally manipulated images for training, again with only a real fake label per image. These two scenarios correspond to weakly supervised training, where we do not have explicit mask annotations. For completeness, we also consider the fully supervised scenario C, where locally manipulated images are used for training together with explicit mask labeling. We maintain the test set fixed and evaluate the localization abilities in each of these scenarios. Our first research question is which of the three proposed methods performs better for weakly supervised manipulation localization. We evaluate the three methods in the three scenarios mentioned previously. Recall that in scenario A, we train on fully generated fake images, while for scenarios B and C, we use locally manipulated ones. Real data from celeb-AHQ is used in setup A and B, while for the fully supervised scenario, real data is not needed. Among the selected methods, we see that patch forensics outperforms the other two approaches across all setups. Localization performance is strong for all methods when training in the fully supervised scenario, C, and it drops as we move to the two weakly supervised scenarios, A and B. Interestingly, GradCam and detention perform better in setup B than in setup A, while for patch forensics we observe the reverse trend. We believe that patch forensics is worse in setup B because here the loss is set at patch level and the patch labels are inherently noisy as we use partially manipulated images at input. Examples of localization masks can be seen in the right side image. On the first row, we show the original image, the impeded one, and the ground truth mask. The following rows represent results obtained in each of the 3 training scenarios for all considered methods. The same conclusions can be observed visually. Very good performance in setup C for all methods. And patch forensics shows good performance even in setup A and B, with B producing noisier masks. Generalization is a key desirable property for deepfake detectors. Our next research question assesses how localization is affected by dataset shifts. To this end, we designed an experiment in which the training and testing data come from different source datasets, FFHQ and CELEB-HQ, while facing the generator and the detection method to patch forensics. In the following table, we observe a constant drop in performance across all scenarios and metrics when there is a dataset mismatch. A closer look at the soft localization maps reveals a more complete picture. The different columns in the figure show that training on FFHQ still produces qualitatively reasonable predictions even for small regions, such as nose and mouth. However, in this mismatch setting, the predictions are less certain at the boundaries and the masks appear to be eroded and with holes. Finally, we evaluate to what extent localization methods trained on a particular generation method, such as diffusion or GAN, generalize to sample produced by a different one. To this end, we use impedance over CELEB-HQ dataset with 4 approaches. Repaint on either P2 or LDM, llama, and pluralistic. We train the patch forensics method in a fully supervised setting, scenario C, on each of the 4 datasets as well as combinations of those. The evaluation is carried on all 4 impeded test sets. In this confusion matrix, we observe that localization works generally very well as long as we test on data generated from the same model, the main diagonal. However, LDM is an exception. Localization in LDM manipulated images is more difficult since the impeding is carried in the latent spans and the decoding step hides the traces of the latent manipulation, akin to how image processing steps degrade detection performance. When we evaluate on data coming from a different generator, the performance drops sharply. See the off-diagonal entries in the plot. The transfer performance between llama and pluralistic is still decent, presumably due to the particularities of the encoder-decoder approach. The diffusion model of repent is different from the two and makes the cross-generator transfer more challenging. On the right, we show an example of the localization mask obtained in the corresponding training text scenarios. The main diagonal results are good with the exception of LDM manipulated images. The off-diagonal masks are low quality and fail to capture the shape of the eyeglasses. In our work, we investigate weakly supervised localization in the context of diffusion-generated images of faces. We explore the importance of different factors in model performance, such as choice of detection method, level of supervision, dataset, and type of generator used. Our key takeaways are as follows. Detection of local manipulations can be performed weakly supervised. The patch-based method consistently outperforms the other 2 approaches, explanations or attention, across multiple settings and metrics. Among the 3 types of factors, supervision, dataset, generator method, supervision seems to have a lesser impact, at least for the best performing method, patch forensics, while the generator impacts the most. Localization of manipulations for the latent diffusion model is very challenging, even in the most optimistic scenario. Our code and data are available at the following link. Thank you.